Folks, I'm working on developing the final. After writing the first page, I can give you this information. I trust you recall, from an acid-base standpoint, we've done a lot with carbonate ion. Not so much with oxalate ion, but a few considerations. It's in our acid-base table, like carbonate ion. As well as the other material forms of these ions. Remember what I mean by other material forms? What are the other material forms of carbonate ion? Hydrogen carbonate ion and hydrated CO2. Or H2CO3 if you want to write a formula for it. Peroxalate ion, hydrogen oxalate ion, and oxalic acid, which is what you get when the oxalate ion captures two H pluses. Each of these anions are showing a charge of -2. So each has the capacity to capture up to 2 H pluses. And the formulas for these species, these ions, and all the other material forms of these ions, all in the acid-base table. Beside acid-base chemistry, what other kind of chemistry did we pay attention to with these ions? Beside reacting in a Bronsted-Miller acid-base fashion, how else did these ions react? Lewis acid-base. We're talking about that now, aren't we? Liganding ability. How else did they react? Which is also arguably Lewis acid-base. You do anything in the laboratory with carbonate ion? What'd you do with it? Beside acidifying.
I dissolved it.
You dissolved it. Beside dissolving it. What's this stuff? Mainly. What is this stuff? Well then, what else you do with carbonate ion in the laboratory? You used it as a precipitating agent, didn't you? Oxalate ion is also usable as a precipitating agent. I haven't included oxalate ion in the laboratory chemistry, but in certain respects it behaves like carbonate ion. It's an effective precipitator of calcium ion, for example. That's pretty much page 1. Now, I'm not going to get any more specific than this. I think that's enough. Now then, back to isomer considerations for transition metal complexes. Very important property of transition metal complexes. 2 categories of isomers: structural and stereo. Structural we began to discuss yesterday. Now, from a geometry standpoint, these 2 coordination complexes are the same. They're each octahedral. But structurally or compositionally, they're different. Here I got 5 ammonia molecules and 1 sulfate ion, coordinated to cobalt in the +3 oxidation state. These are the 6 ligands in the first coordination sphere. Whereas, by ionization phenomena, in other words, if this stands in water solution, chloride ions can migrate into the first coordination sphere while sulfate ions migrate out of the first coordination sphere. We might also expect ammonia to possibly be replaceable by chloride ion or sulfate ion in the first coordination sphere, but I doubt that this is observed because ammonia is a much stronger ligand toward cobalt in the +3 oxidation state than either chloride ion or sulfate ion. We've talked about some of the reasons for that, and we'll talk more about that today. So it's not likely that ammonia gets replaced in the first coordination sphere. At least I have not seen any accounts of such by way of reading papers of experimental investigations on materials like this. So, 2 octahedral complexes of cobalt, each with 5 ammonia molecules in the first coordination sphere. What's the difference? Sulfate ion in the first coordination sphere, chloride ion in the first coordination sphere. So compositionally, these complexes are different. And we talked about distinguishing between such by methods that you've learned about in 46 laboratory. The water solution of this one would readily show precipitation of silver chloride, whereas a water solution of this one would readily show precipitation of sulfate ion, as, for example, barium sulfate or calcium sulfate. But barium sulfate is easier to form than calcium sulfate because barium sulfate is less soluble. Hydrate isomerism. You looked at bonus quiz 3? Any consideration put to you on bonus quiz 3 about the possibility of hydrate isomerism? Well, I'll leave that for you to answer. You've got the bonus quiz, I trust. Take a look at these 2 complexes of chromium in the +3 oxidation state. They are again each octahedral complexes. Here's hexaquo, chromium +3 complex ion. Here's pentaquo, monochloro, octahedral complex of chromium +3. What's happened? It's really like ionization isomerism, except that it involves water molecules in water solution. So we'll call it hydrate isomerism. And water molecules are not ions. On standing, the possibility exists for chloride ions to migrate into the first coordination sphere, and in so doing, replace water molecules while maintaining octahedral geometry. Or if I start with this one, chloride ion could migrate out of the first coordination sphere while water molecule migrates back in, regenerating this. In this stuff, the water molecule that's part of the composition of this is rather like water in the composition of gypsum, which we talked about in brief yesterday, and which you have also studied to some extent by way of laboratory work, 46L assignment 3. These are lattice waters. They're not coordinated waters. These hydrate isomers. If you were in the laboratory and assigned the task of distinguishing between these materials, if, for example, I gave you a sample and I said it's either this or this, what might you do to find out which you were issued? What might you do?
I precipitate out AgCl and then check the color to see if it matches CR.
Color?
Well, yeah.
Did you say color?
Yeah, don't they have different colors?
These 2?
Yeah.
I expect they do.
Yeah, so...
But I haven't given you the color information. So if you see one of these, if I give you one of these complexes, but I don't tell you anything about color, then you won't know which is which by color. But you could look it up. Yeah, that's fair game. Okay? And if the color information is not available, one method you have is by precipitation of chloride ion with silver chloride. But now you've got to be careful with this. This is a quantitative rather than a qualitative investigation, isn't it? Because both of these show ready precipitation of silver chloride. What's the difference? Per mole of this, you get ready precipitation of 3 moles silver chloride, whereas per mole of this, you get ready precipitation of only 2 moles of silver chloride. So now you'd have to weigh some of the sample before you dissolved it in water to see how many moles of the sample you have. Then after you precipitated the silver chloride, you'd have to separate the silver chloride, weigh it, to see how many moles of silver chloride you made. Then with some simple stoichiometric calculation, you could find out which of these compounds you had analyzed. Now then, another method, which you really didn't learn about in 45 laboratory, 46 laboratory, but which I'm sure you'll study about in analytical laboratory. How many of you are going to study analytical chemistry? Okay. By way of a procedure or a methodology known as gravimetric analysis, you'll find out. Well, before we talk about the experiment, I'll ask you, do you think by heating a compound which contains water in its composition, you can cause the compound to lose water? Do you think by heating a compound that has water in its composition, you can cause the compound to lose water?
Yes.
Yeah. Which of these compounds on heating do you think will much more readily lose water? The bottom one. Because in the top one, all the water molecules are strictly coordinated. That'd be a delicate, difficult experiment to conduct, because you'd have to know something about, for example, the temperature at which this loses water. You can make this lose water too, but you'd have to heat this one to a much higher temperature than you'd have to heat this one to get this lattice water to disappear. So that's not a method which I would expect you to be able to put to use at this stage of the game. But there is another method, a method which is more direct and simpler than the chloride precipitation procedure which we just talked about. A method you learned about in 2045 laboratory. What might this method be?
Conductivity.
How about that? A mole of this. How many moles of ions per mole of compound? 4. 1 mole of complex, which is a +3 ion, 3 moles of chloride ion. How many moles of ions per mole of this compound? 3. So again, you can measure a quantity of the sample for analysis, because they have the same formula mass. So you know how many moles of stuff you're starting with. Then you'd have to do some investigations in lab, like you did in 45L, to get a handle on the difference between the conductivities of a solution which has got 4 moles of ions versus another solution which has got 3 moles of ions. Which solution is going to be more conductive? Which one? The one with more moles of ions. So, with a little bit of arithmetic based on conductivity investigation, which you did in 45 laboratory. Remember the salt sucrose mixture I asked you to analyze? That's what it was. I was wanting to see if you folks could apply your presumed knowledge of stoichiometry in conjunction with making conductivity measurements, very simple conductivity measurements, to determine the composition of the salt sucrose mixture which you were issued to analyze. Because the sample is entirely water soluble, but will reflect the conductivity based strictly on the percentage of sodium chloride in the sample issued. If I give you pure sucrose, no conductivity. And one more type of structural isomers, linkage. This is in reference to the bonding shown by the ligand to the metal to which the ligand is coordinated. Look at these two materials. These are identical from a composition standpoint, but they're different structurally because in this complex, cobalt nitrite ion bonding is between nitrogen from the nitrite ion and cobalt. Whereas here, Nitrite ion cobalt bonding involves oxygen atom from the nitrite ion to cobalt. So, if you had methods of investigating bond lengths, bond strengths, stretching frequencies, stuff like that, which you'll learn about in organic chemistry when you talk about infrared spectroscopy. You'd have ways to distinguish between these. But right at the moment, there would be no simple way you could distinguish between these two isomers, which vary by way of linkage behavior of nitrite ion. But we can at least take a look at the Lewis picture for nitrite ion, and in so doing recognize how this thing can show linkage isomerism, because it's got non-bonding electron density on its central nitrogen atom as well as obvious non-bonding electron density on its peripheral oxygen atoms. So you have two different donor sites, the nitrogen atom or either of the oxygen atoms, which of course are electronically equivalent for the nitrite ion. Resonance. Tell me, would you expect nitrite ion to preferentially coordinate through nitrogen or through oxygen? If you go to the laboratory and you synthesize this stuff by putting together ammonia molecules with cobalt in a +3 oxidation state and nitrite ion, would you expect to get this complex or this complex? Here, coordination through nitrogen. Here, coordination through oxygen. Which one would you expect to get? We got to vote for this. Tell me why. You know that was coming.
Nitrogen is less electronegative
Then,
oxygen.
and therefore,
It doesn't stabilize charge density.
it's a better donor.
Yes, exactly.
Hey, for example, parallel case. Two molecules. Molecules whose chemistry we've considered quite often this term. This has got twice as many non-bonding electron pairs. Here we got a whole lot more oxygen-based non-bonding electron pairs. So statistically, you'd probably bet on oxygen. But there's a hell of a lot more going on in chemistry than statistics. We have to pay attention to behavior, which is rarely dictated by statistics. One non-bonding pair, two non-bonding pairs, yet this is a much better H+ grabber, and it's also a much stronger ligand, because this is a better donor atom than this. And then, shortly, when we talk further about thermodynamic stability of the coordinate covalent bond, we'll provide another reason why this is, in most cases, a much stronger ligand toward a transition metal ion than is this. Now then, another reason. We talked about the fact that this is a superior donor based on electronegativity. Is resonance a valence electron stabilizing property of a species? Is resonance a property of a species which stabilizes its valence electron density? Absolutely. If this thing coordinates through nitrogen, does it lose resonance? No. What if it coordinates through oxygen? Then what happens to resonance? Resonance goes away. That's not an electronically favorable process. For example, If one of these non-bonding pairs becomes a bonding pair, here's my metal, Mn plus. All right? If I now do formal charge analysis, when the oxygen has 3 non-bonding pairs, its formal charge is -1. But after bond formation takes place, what's the formal charge on oxygen? 0. And now what's the formal charge on the coordinated metal? It's N-1 plus. This gained a unit of negative formal charge, while this lost a unit of negative formal charge, and now no more resonance. So if you had the wherewithal to study bond lengths and strengths in nitrite ion, you know for the free nitrite ion you're going to find these NO bond lengths and strengths to be equivalent. Shorter, stronger NO single bond, longer, weaker NO double bond. But if this baby coordinates through oxygen, then you're going to find an NO single bond and an NO double bond. These lengths and strengths will no longer be anywhere near the same. Okay. Now I've posed here a question for you. In considering ligands, which you did with the discussion folks on Friday, a common ligand is the thiocyanate ion, SCN-, or the isothiocyanate ion, NCS-. Notice that all I've done for the thiocyanate ion and converting it to the isothiocyanate ion is to imagine that here the principal degree of negative charge density is on the nitrogen atom versus here on the sulfur atom. What would you do for this ion? What did you do on Friday to find out which of these formulas appears to be most reasonable for this ion? What'd you do? Well, how'd you do formal charge analysis? How about that? You think you might need to draw Lewis structures for this exam? If you can't draw Lewis structures, don't even bother to show up. Waste your time. You're lost. So I'll let you pay attention to the Lewis structures for these. And maybe your discussion TA asked you about this on Friday. If I'm using this as a ligand, and I make coordinate covalent bonds with iron plus 3, would you expect the bonding to be with this species and the coordinate covalent bond interaction through nitrogen with iron plus 3, or do you think it would be through this? How many of you did this? How many of you did assignment 10? This term in 46 laboratory. Assignment 10. Well, then you use this stuff. You remember? Did you find out that when thiocyanate ion coordinates with iron plus 3, you get a deep blood red type color? So you did this investigation. Now in the laboratory manual, I didn't ask you to think about bond structure, because unless the person in 46 lectures making a point of this, the question isn't going to mean much to 46 laboratory students. And I don't think anybody who does 46 lecture talks about this stuff, except, guess who? On the other hand, if I use this as a ligand and I got a water solution containing silver ion, and I find out that this as a ligand readily coordinates the silver ion, do you think the coordination is through the nitrogen end or the sulfur end? Well, before we talk about explanation, which for the immediate moment I'm going to leave up to you, let's do the vote business. This one with iron 3, which N? N or S? How many vote with N? Those votes are right. With silver plus, how How many vote for S? Based on the chemistry we've considered this term. Based on chemistry you did in laboratory. What did you find out about the propensity of silver ion to react with sulfide versus nitrogen? Or sulfur versus nitrogen? Sulfur containing things versus nitrogen containing things. What'd you find out?
Sulfur is much more stable.
You're damn right. You make the silver ammonia complex ion. That's a very stable complex ion. You put a source of sulfide ion in there, silver ammonia complex ion converts quantitatively to silver sulfide. All right, so you know the answer. Through nitrogen with this, through sulfur with this. Now you think about the why of it. We'll talk further about the why of this when we get through this isomerism consideration and then begin our conversation of thermodynamic stability of the coordinate covalent bond. But you already should have some pretty good ideas on this. Okay, enough on structural isomers. Now, a particularly important and interesting isomeric consideration. Stereo isomers. All stereoisomers are geometrically equivalent. They're structurally equivalent. But they're different. Like cis-trans, which we've already looked at. Okay? Another very simple example of a stereoisomeric complex. One which perhaps you talked about in discussion class. I expect that you did. Consider this complex, which, since the complex, shows an oxidation state of 0, means this is a complex of platinum in what oxidation state? What's the oxidation state for platinum in this material? +2. How many valence electrons does platinum in the +2 oxidation state have? It's in the nickel family. The nickel family of atoms, as 0 oxidation state species, all have 10 valence electrons. D8S2 for nickel, D10S0 for palladium, D9S1 for platinum. Oh boy, goofies. But all 10 total valence electrons. So how many valence electrons for platinum in this stuff?
16.
I'm not counting, I'm just talking about platinum 2 by itself. 8. What is the configuration for these 8 valence electrons? In what valence orbital or orbitals do these 8 valence electrons reside? Nickel, period 4, valence electrons are 3d. Palladium, period 5, d valence electrons are 4d. Platinum, period 6, what are the valence d electrons? Valence d electrons are in what energy level? 5. So this has a 5d8 configuration for the platinum 2 species itself. (5d8). All right? Now, we've recognized the configuration for the metal itself. This business of krypton configuration, that doesn't work for materials like this. Because this is a common positive oxidation state for platinum. It's those unusually low oxidation state for complex metals where that krypton 18 electron count works. Not for materials like this. If I tell you, though, that this stuff is diamagnetic, now you can tell me how these 8 5d valence electrons are configured. And you can also tell me how platinum in this stuff is hybridized. How are the 8 5d electrons configured? Are there any half-filled d orbitals? It's diamagnetic. There's the metal d electron configuration. Now let's fill in the remaining part of this configuration by putting in the non-bonding pairs from the 1, 2, 3, 4 monodentate ligands, which therefore make 4 coordinate covalent bonds. Each ligand converts a non-bonding pair to a bonding pair on bond formation interaction. 2 ammonia molecules, 2 chloride. Again, we make this kind of drawing so that you can recognize which of these valence orbitals by platinum became occupied by electron pairs from ligands to make these coordinate covalent bonds. So what's the hybridization? DSP2. What's the geometry? We talked about this the other day. Square planar. We even reflected on the orbitals which were used to construct this DSP2 hybrid. And recognized that the lobes of the d orbital, as well as the lobes of the 2p orbitals that are part of this hybrid, all share the property of lying in the same plane. So this thing is planar. D x squared minus y squared s and px and py. Okay? So if I want to draw a picture of this complex, all I got to do is draw a square. If I want Cartesian coordinate reference axes, I'll put them in like this. Here's platinum at the center of this stuff. And now, where can I locate the chloride ion ligands and the ammonia molecule ligands? Well, I can put the chloride ion ligands here. That makes the ammonia molecule ligands here by default. Or I can put the ammonia molecule ligands trans to each other as opposed to cis. So this is showing geometric cis-trans stereoisomerism for this complex. Would this thing show geometric isomerism, cis-trans isomerism, if it was tetrahedral? Imagine platinum in the +2 oxidation state in the center of this tetrahedron. Does this show cis-trans isomerism? Hell no. There's no cis-trans for this thing. All the bond angles are 109.5 degrees. But here, the bond angles are 90 degrees and 180 degrees respectively, aren't they? Different bond angles. If you were issued one of these complexes and you had the ability to make the measurement, what measurement would you make to find out if you had the cis complex or the trans complex? Yeah. Which one is polar? This one. Have you ever heard of this stuff? Cisplatin. This is it. You ever heard of it? It's shown a lot of therapeutic value in cancer research. How about that? Look it up if you want. Cisplatin. Google. You'll get all kinds of information. I'm sure Wikipedia is loaded with information about this stuff. So we just talked about it. From a chemist perspective. Not from a medical perspective. But the medical perspective is clearly quite important. All right? Now then, let's start to have some fun with this stuff. Let's go to question 2416. You see the complex. Diaquo, diamino, dichloro, cobalt 2. Since the complex itself is a compound and has zero oxidation state, and it's got two anionic ligands in it, each of which bear a charge of -1, the oxidation state for cobalt in this stuff is +2. Now, in order to make pictures quicker than writing waters and ammonias and all that stuff, I'm going to play this. Get it. ABC. No, wait. For my models, I got greens and purples and whites. Greens and purples and whites. Greens, purples, whites. Okay? Greens, purples, whites. Question. Over here, we've noted, which is in the notes. I didn't write anything here which is not in the notes, except this term. We'll see there's a special subcategory of geometric isomers which are known as diastereomers. More on those in a moment. Let's jump to the second subcategory of stereoisomers, optical or mirror image isomers. I'm sure you're familiar with these, even though you may not have thought about them very much. I would expect at many times during your livelihood, you've stood in front of a mirror and shown your left hand to it. If you haven't done this, do it. And show your left hand to a mirror. Open hand, palm facing the mirror. What do you see looking back at you? A right hand. How about that? Every material object, so long as it's not transparent, casts a reflection in a mirror. Nothing fancy about that statement. Is the image of the object the same thing as the object itself? That's the $64 question. Is the right hand the same thing as the left hand? How do we find out? We subject the object and its image to a test called superimposition. I take my left hand, hold it this way if you will. I don't have to, but I'm going to do it for my superimposition test. And I'm going to take my right hand. I'm going to lay it over my left hand. And immediately I see the positions on the overlapped hands show that the thumb and small finger positions are different. What's that tell me? The left hand and its mirror image, which is the right hand, are in fact different. They're not the same. Now, if I take a sphere and show a sphere to a mirror and I see the sphere looking back at me, Now I have a case where the mirror image is the same thing as the object whose image was cast. Now, if the object is different, like the left hand, right hand, I have discovered a property called optical isomerism. I have discovered that my left hand, as well as my right hand, because if I show my right hand to a mirror, see a left hand looking back at me. My left hand, like my right hand, are chiral. Ha ha! That means optically active. You will talk, for example, in organic class, very often about chiral carbons. That means, is the carbon atom in question, plus the groups which are immediately bonded to the carbon atom, showing a mirror image, the carbon atom and the groups immediately connected to the carbon atom. Is the mirror image of that carbon atom and the groups connected to it the same or different? If it's different, that carbon is said to be chiral. Take a look at an example, simply because you're going to do a whole bunch of this stuff in organic class. Carbon with atom A, B, C, D. Up. Let's make it E. I don't want two carbon atoms. This is tetrahedral. It has the same shape, this thing, the same structure as a methane atom, a methane molecule, pardon me. But if I take the methane molecule, formula usually written like this, but based on relative electronegativities, ought to be written like this. But we'll live with either. And I do some chemical substitution on 3 of the 4 of these hydrogen atoms. Replace one with a bromine atom, another with a chlorine atom, and another with a fluorine atom. Then I make a molecule which is compositionally like this. Central atom carbon with 4 different peripheral atoms. Is the mirror image of this? Is the mirror image of this the same as this, or is it different? You remember looking at this in Chemistry 2045 laboratory? Glad you look at this too. Because it's important. Now, tetrahedron. Atom, atom, atom. These are all includable in the drawing surface. So if I imagine this to project this way toward me, then this is projecting behind the drawing surface. So I can show that like this. At least this is one way to show it. That means behind the drawing surface. Let's take a look, because this is important. Now here, I'm showing you a very special ammonia molecule. It's special in that I've taken 2 of the hydrogen atoms and replaced them with different atoms, like chlorine and bromine, like I did for the carbon atom. So imagine this is a material derived from ammonia. Here's its non-bonding pair. There's the nitrogen central atom. And one of these is hydrogen and the other atoms are different. Whatever they are, who cares? Okay? Is the mirror image of this the same or is it different? Now let's see if we can, while you're thinking about this, take a look. Let's see if I can quickly manufacture another model. Enough red ones. terrible. All right. We'll take away the red one. Steal one from here for a moment. Put on a white one. Okay. Then we got this. And this. And this. And we'll steal a white one. And we need a purple one. Okay. Oops. Need a bond. Oh, we even got a same colored loop. Okay. There we are. Two ammonia type molecules which are obviously the same shape and the same composition. sp3 hybridized nitrogen. Tetrahedral geometry for the valence electron pairs of nitrogen. But the shape of the molecule itself is trigonal pyramidal. This stuff you know about. Are they the same? Or are they different? Well, let's try the superimposition test. Superimposition shows green, green, purple, purple, white, white, loops at the same position. Of course, central atoms overlap each other. So these are identical, aren't they? All right. Well, let me go back to one of the molecules. It doesn't matter which one. And all I'm going to do is to break and remake two bonds. I'm going to break this bond, and I can break this, this, or this. It doesn't matter. I'll break this bond. So what I did for this version of this molecule is to interchange the positions of the white atom and the green atom relative to where they were originally. Well, your horse sense ought to tell you these can't possibly be superimposable now. Okay. Whites match, the non-bonding pairs match, the central atoms of course have to match, but look what happened here. So, what I achieved with that bond break remake process was to turn this into the mirror image of this. Let's see if that's true. Here's a mirror, a reflecting surface. I'm showing this to the mirror and this to the mirror. What do I see? The green ones are each at the top in the mirror. These are each out to that side. These white ones are each projecting toward me and away from you. And the loops are each projecting trans with respect to each other. Do you agree? These are mirror images of each other? And they're not superimposable. Is this nitrogen chiral? Is this nitrogen optically active? Is the mirror image of this nitrogen and the groups connected to it different from this itself? Here's its mirror image, and this is different. It's just like left hand, right hand. Same thing. In fact, the left hand, right hand is really geometrically more problematic than this. Because left hand, right hand, I got 5 things attached.
So it is chiral.
These nitrogens are chiral. Now, whether or not I turn this into the same thing, it doesn't make any difference because the mirror image of this is different from this. So this is a chiral nitrogen. Statement. If an atom and the groups connected to it. So here we're looking at this nitrogen atom and these 1, 2, 3 atoms connected to it plus this non-bonding pair. So we'll consider this a group connected to nitrogen. It's non-bonding pair connected to this nitrogen. If an atom and the groups immediately connected to that atom show a mirror image which is different from the atom and the groups connected to it, That atom is chiral. It's optically active. And that's how you find out if something shows true mirror image isomerism. It's like showing your left hand to a mirror, seeing your right hand looking back at you. Okay? So we told you what chiral means. If you want a more elaborate definition, you can look it up. And I believe you've seen the word chiral on bonus quiz 3. And you've seen a question about whether or not an sp2 atom can be optically active. And I even told you a molecule to look at to give you a handle on that issue. All right? Now let's go back to this thing. Tetrahedral, but most coordination complexes are octahedral. So let's go back to consider complexes which show octahedral geometry rather than tetrahedral and pursue the issue of stereoisomerism. Geometric and or optical. To repeat, if I want to represent an octahedral complex on a flat surface, I start with a canted square. I'm going to put the metal in the direct center of the canted square. I'm going to leave that out. Just complicates the drawing. Then I'm going to complete the octahedral structure by putting a line from the center of the square to the top and another line from the center of the square to the bottom. Now here, the square is over this. You can't see it. I mean, I could do this if you want to. Okay? All right? Now let's look at these groups. G, G trans, P, P trans, W, W trans. Versus G, G cis, P, P cis, W, W cis. So here we're looking at all trans for like ligands. And here we're looking at all cis for like ligands. Now we're going to write a statement. If any species, like a TM complex, since we are at present talking about transition metal complexes, is optically active, it will always be the least symmetric geometric isomer. Now I think you can accept my statement that for the two geometric isomers we have sketched for this complex, we have the extreme cases. All trans versus all cis. Extreme opposite cases. Question: which of these is the one of lower symmetry, least symmetric? You know what this word symmetric means? Does it seem obvious to you that the all cis is surely of much lower symmetry than all trans? One way to get at this idea of symmetry, so as to recognize which geometry is symmetric versus another geometry which may not be symmetric is to relate it to polarity. If cobalt is a rock in a farmer's field, and the farmer has 3 different sets of horses. One way he can attempt to move this rock is to tie a rope around the rock and the other end of the rope around the horse's neck. Okay? So you've got 3 different sets of horses. 2 purple horses, 2 green horses, and 2 white horses. All right. So you've never seen white horses, just green and purple. That's okay. I don't mind. Okay? If I tie the horses green, green, purple, purple, white, white to the rock, and now tell the horses to move, will they move the rock? Here? Will the rock move? No, because the green, green pulling forces are equal. They cancel each other. The purple, purple pulling forces are equal. They cancel each other. The white, white pulling forces are equal. They cancel each other. That means this thing would be not polar because it's perfectly symmetrical. But how about this thing? There will be some cancellation of pulling force. That's for sure. Because, for example, the whites, one's going to pull this way, one's going to pull this way, and this pulling this is going to oppose this pulling this way, and this pulling this way will oppose this pulling that way. But if the purple pulls more strongly than the white, and the green pulls more strongly than the white, then the rock will move this way. This one is polar. This one is of lower symmetry. And for a complex of this composition, this is the isomer, the geometric isomer of lowest symmetry. All right? That means, based on this statement, if either of these is optically active, if either of these show a mirror image which is truly different, it's got to be this one. Okay, so far? Now, before we do that, we'll ask another question for these two. How many others? Pardon me, how many other geometric isomers are there? And then we'll add what we're presently considering. And is the least sim for symmetric, the least symmetric isomer optically active. And we've already recognized the least symmetric isomer to be this all cis thing. First question. How many other geometric isomers? What do you think?
6.
How many other geometric isomers?
4.
We got 2 on the board. How many others are there? 4 others? Well, then let's draw. If there are 4 others. You remember the cobalt's in the middle. Let's start with the all trans. Okay? We'll keep green and green trans. Well then, white, white, purple, purple. Okay so far? Well, what can I do to change this into another geometric isomer, which so far we haven't considered? Can I keep the green green as they are? And reposition PP and WW and make another geometric isomer? All right, I'll keep the green green as they are. Now you folks who are insisting I can make another geometric isomer, different from any of that we've seen so far, by keeping green green where they are, tell me where to put the W's and the P's. Because if I put a W here and a W here, that forces the P's to be trans, doesn't it? If I put W here and W here, it forces the P's to be trans, doesn't it? Guess what? If I keep the green greens trans, I cannot draw another isomer. It's impossible. Okay? So after we got this far, I asked you how many other geometric isomers? The only vote I heard registered was 4, and that ain't right. What's the right answer?
3.
3 is right. Where I'll have PP trans and WWGG cis. It doesn't matter, GG, WW cis, those are the same thing. Or I'll have WW. And then GG, PP, or PP, GG, or PP, and GG, who cares? Those are all the same thing. And if you don't believe it, you'll believe it soon when we play with the models. Now let's go back to this thing. And now get you in the habit of drawing mirror images. All cis model, just like what we got on the board. All cis. Statement. Is this model G's cis, W's cis, P, purples cis, is this model the same as this thing? Now notice what this shows. W at the bottom. So we'll put a W at the bottom. And this W over here at a corner projecting toward you, over there. Okay? Here it is. Now over here I got P and P on the left side of the square. Here I got G and P. So this is so far not that. Well, let's put the other white one at the bottom. And this one at the front corner. All right? P, P, what's this? What's this? Is this the same as this? No, it's not. So let's draw the mirror image of this. We'll draw another canted square. And remember, W, central atom, G up top. They're all in the plane of the drawing surface. So I can put them in the picture immediately. All right? These two are closest to the mirror. So they'll appear on this mirror image over here. These two are in this square plane, part of this canted square, but these are furthest from the mirror. This behind the drawing surface, so G's over there, behind the drawing surface, and W over here. Here's the model I showed you. We found out the model wasn't this thing. So it must be that thing. How about that? W, 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 G, G, G up top, G up top. Purple over there, and purple over there. Purple. How about that? Interesting, isn't it?
Would the canted square for the mirror image be kind of oriented to the left instead of the right?
Well, you can orient it any way you want, but I've always done it this way.
I mean, is it like like the same kind of diagonal as the left image, or is it kind of flipped to the other side?
Here's the canted square, right here.
Okay, yeah.
Remember, I draw it like this to show you this square is perpendicular to this drawing surface. And I'm telling you to draw canted squares on bonus quiz 3, and I will tell you to draw canted squares on the final exam. And if you draw this, since I'm going to grade this image stuff, because I'm quickest at it, every time I see this, I'm going to take my red pen and say, because you didn't do what I told you to do. And I'm not going to bust my eyeballs to interpret your picture, which has not been drawn according to directions. See how nice I am? So, just like we showed you with the 2 tetrahedra, with the different atoms substituted on a nitrogen atom after having started with an ammonia molecule, same thing for this. These, if my memory's right, are the same. Let's find out. Greens and greens. Whoops! That's not the same. Maybe when I put them back together, I didn't make the same thing. Well, then they must be mirror images. We'll find out in a moment. It must be the same. Green up top.
Just turn it.
Yep.
No. No, put the other. Oh.
There we go. White, 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 purple, 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 green, 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 green. Okay, there we're the same. All right? We did the superimposition test and find out they're the same. Now, you remember what we did to interconvert? The ammonia substituted, the nitrogen substituted stuff? We took 2 bonds, broke and remade. Now, when you're playing with an octahedron, you have to take 2 bonds, which are cis, break and remake, while maintaining all cis geometry. Okay? So, I'm going to pick on this purple and this white. I put the white over there and the purple over there. That's all I did. Okay? Notice I still have all cis geometry for like ligands. But I did the bond replacement. Now I have the mirror image. This is not this. This is its mirror image. First, let's show you that it's the mirror image. Up. Okay? There's the purples looking into the, here's the mirror. Okay? Green up top, white at the bottom, white at the bottom. The white's out in front of the mirror, projected toward you. These 2 greens in this canted square, projected away from you and toward me. Different. And if you try the superimposition test, you'll find out. There is, the whites overlapped with each other. These greens overlap, these purples overlap. But you see what you got here? They're different. And the hard part of this game for you, right now, is to get in the habit of doing this by drawing pictures. So let me show you one more trick, since we've got these pictures on the board. The point is, after I draw this picture, and its mirror image, how do I prove that this mirror image is different from this when operating on this drawing surface? All right? The answer is, take either one of these. It doesn't make any difference. Hold it by the top and bottom atoms and rotate it 180 degrees. Okay? Here's what I'm doing. Top atom, bottom atom. Look what happens to the atoms in the canted square. You see the 2 whites looking at you? I'm going to do a 180 degree rotation. Now the 2 whites are looking at me. Okay? So that's what we're going to do. So this one is closest to me. I'm going to take this and rotate it 180 degrees. I'm holding it by the top and bottom atoms. So this is my axis of rotation. So green stays where it is and white stays where it is. The only atoms that move are those in this canted square. Where does this W become if it moved 180 degrees? Here, here, or here? Yeah, good. They all go to trans positions relative to where they were. P goes over here, G goes over here, and the other P goes over here. Okay? Now then, this is the same as this. I took this and rotated 180 degrees, just like the wind blowing this thing in space. But take a look at this compared to that. Look at the two purples. They're on the left side of the Cannon square, just like that. Green up top, just like that. W down below, just like this. But look at the W and G. W behind, G out in front. Here, W out in front and G behind. And that's the game you got to learn to play. We'll do a lot more of this tomorrow.